back, everybody, to the second session. Our first speaker is Gavin Pringle from the Edinburgh Parallel Computing Centre, and talk to us today about current hardware for HPC, HPC, and data management from BioMed.
Hello, my name is Gavin Pringle, and thanks Herman. I work for EPCC, one of the partners of CompBioMed, and I'm going to talk about the current hardware available for high-performance computing, high-throughput computing, and data management for CompBioMed. There are a number of resources available, and I have 20 minutes, and obviously you don't want to hear of a list of hardware, so I thought I'd just take this opportunity to stand back a moment to try and simplify high-performance computing, so that, particularly for the non-HPC experts in the audience, so that we can all have a common terminology. So this is going to be very high-level, cartoon, Mickey Mouse description of high-performance computing. So, getting access to resources, I'll start with, so that CompBioMed has been granted allocations on several large HPC resources, and allocations of these resources are managed centrally through this email. So if you're keen, you can email that address. But first, high-performance computing, broadly described. A high-performance computer is a single system which has several nodes, or boxes, or mainframes, or sockets, or big lumps of iron that has a single door to it. So these nodes can be a number of 2 to tens of thousands of nodes. Within each node, you'll have a number of processing units. These are called cores, and these cores can be CPUs or GPUs. CPUs, you can have between 2 and 68 CPUs inside a single node. For instance, Intel Knights Landing has 68 cores per node. Or with a GPU, it's a much greater number, 500 to 4,000 GPU cores within a single node. And all these cores inside a single node share the memory available to it. And then on a larger level, so you have the cores inside the nodes, and then the multiple nodes are connected together with some sort of communication cable. This is called the interconnect. Sometimes it's called the communication fabric. And there's several types of these. Some are slower, some are faster. And all of this is essentially a high-performance computer. And it does two things. It computes and it communicates. Hopefully you spend more time computing than communicating. The computation is done by the cores, and this typically in high-performance computing is done using computing languages such as Fortran, C, C++, and to a larger and larger extent these days, Python. So you'll notice there's no MATLAB, or R, or Excel listed in this. And then there's the communication. So the cores themselves communicate, perform the computation, but they also have to exchange information between themselves. Now this is very fast inside a node, because they all share the same memory. But it's slightly slower when you go, or significantly slower, when you go between the nodes over the interconnect. And indeed slower again when you want to write data from your local memory onto disk. And then finally, managing your job. So jobs are submitted via a job manager, and this is called a batch system. Commonly used batch systems are PBS, LSF, Slurm, Load Leveler, and to a lesser degree SGE, Sun Grade Engine. And then what is cloud HPC? This new term, essentially a very rough sketch could be that there's on your laptop or your workstation or your PC, there's a client running there, and you can submit a job that runs remotely on a distant HPC system. You kind of don't care where it is. So it will take the data from your laptop, put it onto the large machine, manage the job for you, and then take the data back once the job is finished. That essentially is cloud computing. Now I should say this is a very simplistic view of both HPC and cloud computing, but it's just to get everybody in a room a bit more up to speed into the same level playing field. So the essentials of HPC, or high performance computing, is that typically it is a single, very large application, and it uses a huge number of cores that use multiple nodes, and it requires a very fast interconnect. And then you have high throughput computing, which is typically ensembles, or what we used to call task farms. So every little job, so there's a small to medium-sized jobs. They each run on a large number, not a huge number, a large number of cores. But these jobs can run simultaneously, and you don't need a fast interconnect for such jobs. And then lastly, data management essentials. So typically, a data management platform will be running serial jobs, but will be associated with a very large shared memory resource, what some people call a FAT node. So that'd be a large number of cores, but huge shared memory space. And data management platforms will also have a very fast interconnect to disk, much faster than other HPC or HTC platforms. So, what do we have available to us at CompBioMed for these three types of systems? So for HPC, we have tier 0 platforms. I should perhaps describe the terminology here. We have tier 0, tier 1, tier 2, tier 3, tier 4. These describe a kind of pyramid of computing resources. Tier 0 is the very top. It's typically a very large supercomputer that a single country can't afford. Then tier 1 would be a very large supercomputing system that a single country can afford. So that would be like Archer in the UK, for instance. And then tier 2 would be something perhaps more bound to a university. So for HPC, we have two machines in tier 0 currently available. That's Mare Nostrum in Barcelona and Marconi in CINECA. I've put LRZ SuperMUC in grey there. It's not currently available across CompBioMed in general, but Peter's working on an application to get the allocation. Tier 1 platforms, we have EPCC's, or the UK's Archer service, and Cartesius in Surf Sara. And then the tier 2 service, is really more tuned to high throughput computing. So the interconnects might not be so fast, but you have direct. So the two systems we have for high throughput computing are Cirrus at EPCC and LISA at Surf Sara. And then lastly, for CompBioMed, for data management, we have Archer's, or the UK's research data facility, I should say, which is attached to Arthur. And this is the RDF and the DAC. So I'll run through these one by one. So on a very, very general basis, so we don't get overloaded with technical detail. So this is Mare Nostrum. It's one of the nicest supercomputers in the world. I think it resides inside a church. It used to be, after it was a church, it was a theatre, and they have these velveteen red seats up on the wall, and they use that to bring in the politicians, and they sit in the red chair, and then they have a light show. It's all very impressive. And the computer itself is in a glass box. You can't see it in that photograph, but the cooling is also, underneath the machine, is also in the glass box. So it's very nice to look at. Anyway, so there's 48,000 or 496 cores in total. These are Intel Sandy Bridge cores. And there are 16 cores per node. And the interconnect is InfiniBand. And the cycles available to CompBioMed is 150,000 core hours. Now there's lots of information missing from this slide that I think isn't necessary for a very general understanding of what HPC is. We don't have the memory per node, because that varies. It's a heterogeneous cluster, so some nodes are bigger than others. It also has Intel Xeon Phi processors, sometimes called Knight's Landing. But we don't have that as part of our allocation to CompBioMed, so I haven't listed it here. Anyway, the next, these are alphabetical, by the way, just so I don't offend anybody. But these are all in, so these are the tier 0 resources. And the next one is CINECA, the Marconi. This is through Prace, and this is calls 12 and 13 lumped together. And we have, it's actually 2 machines. One is a 27.875,000 Intel Broadwell cluster. And then they have the Knight's Landing cluster, which is a smaller number of cores. And they have 36 cores per node for the Broadwell and 68 cores per node for the Knight's Landing. In some sense, Knight's Landing is halfway between a GPU and a regular Intel Broadwell, for instance. There's a lot of cores sitting on there, but if your computation is memory bound, so you don't have enough sums to do, you're trying to pull the data onto you can't pull the data onto the node fast enough, then the performance isn't so great. So Knight's Landing is you have to for a particular simulation it might work very well on Knight's Landing, but it might be very poor on GPUs. Or another simulation might work well on GPUs, but not so well on regular high-performance computing. Anyway, that was a sidestep. So the interconnect that Marconi uses is Intel OmniPath, which is actually different from every other HPC system we have access to. They're all InfiniBand or Aries. And the cycles available to the Center of Excellence in general is over 81,000 CPU hours, but that's only until the end of August this year. This is a Prace, available through Prace, and it's the only external resource, i.e. not from a partner or an associate partner, to CompBioMed. Then we have LRZ SuperMUC. Again, I put this in grey because this isn't currently available, and my talk is about what's currently available. Total number of cores are over 241,000, and they have a mixture of Intel Xeon Sandy Bridges, Westmere, and Haswell Xeons. The number of cores per node varies. The interconnect is InfiniBand. Hopefully this will come online soon. And then we drop down to tier 1, and this is Archer at EPCC up in Edinburgh. It's a cluster of Xeons and Xeon Phis. Knight's Landing, Xeon Phi, it's the same thing. And we have 64 cores per node, and the interconnect is Aries. This is a Cray proprietary interconnect, and it's extremely fast compared to the speed of the chips. And the cycles available there are 1.9 million CPU hours on the Xeon and 28,500 CPU hours on the Xeon Phi. And then Cartesius at Surf Sarah, that's the other tier 1 platform we have access to. This is a very heterogeneous machine. It has Knight's Landing units, it has GPU, it has regular multi-core processors. So the number of cores we have on the machine available to CompBioMed is, that can't be right, there's a number missing, so it's almost 41,000 cores of the Intel Broadwell, and 132 nodes, that can be right either, of GPU, sorry. And the number of cores per node varies depending on whether it's GPU or the Broadwell. Again, it's InfiniBand, and the cycles available to CompBioMed in general are 1 million CPU hours. Then dropping down to the high throughput computing, so this is a tier 2 machine, much smaller. This is 2,000, just over 2,000 CPU cores. So we're going much smaller, but it's much more, shall we say, accessible. There's not when you submit your job into the queue, you'll run very, very quickly. It's more, this machine is more business orientated. So we don't look for 96% utilization, because that just means that you're going to have days waiting in a queue. So we'd rather see 50% utilization, which means anybody can, when they log on, their jobs will run. So it's more of an urgent computing environment. So we have 36 cores per node, we have InfiniBand again, and on this machine we have 40,000 CPU hours. I should say that all the cycles I state are per annum. So next year we'll have another 400,000 core hours. And that's for all the platforms. And then the other tier 2 system we have access to is Lisa, also in Amsterdam at Surf. It's slightly larger than Cirrus, over 7,000 Xeon cores. And they have 2 types of nodes. They're connected with InfiniBand, and there again the annual allocation is 700,000 CPU hours. 5 minutes. Okay, thank you. So lastly, the data management. Our intention are for people to do their pre and post processing work, which is typically done with serial codes that needs a lot of memory. And so this hangs off Archer very closely, but it's a UK facility, so everybody can use it. So the RDF is the storage unit, and the DAC is the computational element. The DAC is the data analytic cluster, and that's 304 cores, a mixture of Ivy Bridge and Westmere Intel processors. And we have either 20 or 32 cores per node, connected with InfiniBand again, and it's currently free. If you are an Archer user, you get free processing power for your pre and post processing requirements, if you like. And this data facility has a very fast connection to the RDF, or the Research Data Facility, or I should say the UK Research Data Facility. It has 23 petabytes of usable storage with a further 48 petabytes of backup. And all nodes are high bandwidth, direct InfiniBand connections to the RDF disks. That should be all the DAC nodes have access to the RDF disks. But again, if you're running on Archer, then you can use the DAC for pre and post processing. And again, it's currently free. So just a couple of notes on all of these platforms. All of the cycles stated are per annum, except for Marconi, which I've already said. For all of them, industrial partners need special permission to access it, and none of them can be used for commercial purposes. This is except for EPCC Cirrus, because it is actually an industrial-facing, cloud-based HPC system. So we want people to use it for commercial purposes. And indeed, it's quite underused at the moment, so when you submit a job it'll run quickly, but there's an idea of urgent computing where maybe you need your results tomorrow, or more urgent, you need your results in an hour, or yet more urgent than that. And so we're looking at the American system of introducing tokens, where a weak token will put you to the top of the queue, and a stronger token will swap all the running disk jobs to disk, and your job will run immediately. So we're looking into introducing that as a feature. So 2 more slides. So how to access your HP service of choice. I mentioned this already. That's the email address, centrally managed by UCL. And when you apply, you have to state which machine you'd like to use, the size of the allocation that you would want. Don't grab all of it, it's to be shared. A brief description of the problem to be investigated, and the list of the codes that you wish to be employed. I should add that a lot of these HPC services aren't just cycles, they're also people. So you might want to have your code parallelized or tuned for a particular platform, or better still, tuned to be portable and parallel. So all the academic departments offer that service as part of your allocation. And the URL there is for just an exhaustive list of what is currently available. And that's it. Do you have any questions?